Okay, thank you very much for the invitation. In this talk, I'm going to discuss non-planar corrections to anomalous dimensions of primary operators in ABJM theory appearing from semiclassical M2-Branes. And this talk is based on two works published with Simona Giombi and Arkady Tsetlin, and with Matteo Beccaria and Arkady Tsetlin. So in gauge theories such as n equals 4 Sapien Mills or ABJM theory, anomalous dimension of operators in 1 over n expansion may be written as a function of lambda at each order in 1 over n. The leading term, which is just the planar part, is controlled by integrability and in principle can be determined as exact function of lambda. Less is known about non-planar corrections. For instance, in the case of n equals 4 Sapien Mills, they are computed at weak coupling. For instance, for cusp anomalous dimension, the non-planar correction appears at the fourth loop order, and similarly for Caniche operator, in n equals 4 Sapien Mills appears.
Attention, please.
Sorry.
Attention, please. The fire alarm is about to be tested. Please take no action.
Okay.
Attention, please. Attention, please. The fire alarm is about to be tested. Please take no action.
Okay, so coming back to non-planar. Okay.
Attention, please. Attention, please. The fire alarm test is now complete.
Okay.
Please respond to all future fire alarms.
Okay. So I guess that means that we can continue with non-planar corrections at weak coupling. So they're computed in n equals 4 Sapien Mills for cusp anomalous dimension and Caniche operator. Both appear at the fourth loop order, and by making an analogy, and less is known about ABJM theory, but by making an analogy between these two theories, one can also expect that for these quantities, the non-planar corrections will appear at the fourth loop order. Much less is known about strong coupling, and there are no predictions for anomalous dimensions from the gauge side. However, one can consider another quantities which are protected by supersymmetry, such as, for instance, free energy or BPS-Wilson loops, for which the result is known from localization, which is exact in both 2 coupling and also n. It was recently shown that M2-Branes, well, semiclassical approach to M2-Branes in both ADS4-S7 and also ADS7-S4 reproduce the leading terms for these protected quantities. Well, in particular, 1/2 BPS-Wilson loop, instanton contributions to the free energy in both 3-dimensional ABJM theory and 6-dimensional 2,0 theories. This provides a motivation to apply the setup to non-protected quantities such as anomalous dimensions by using this semiclassical M2-Brane approach. So in this talk, I'm going to review the semiclassical M2-Branes and consider one of the examples where the result is known on the gauge side, which is 1/2 BPS-Wilson loop, and then I'm going to explain how to apply this logic to anomalous dimensions. So let me start by reviewing the action for a supermembrane. So the supermembrane action of the Green-Schwarz type was suggested in the paper of Bergshoff, Seshkin, and Townsend, and its bosonic part describes a 3-dimensional surface interacting with Ramon-Ramon field. One can add fermions by considering L11D superspace, which contains 32 components Majorana spinors. And the action also contains the so-called like Vezumino-like term, which can be expressed as an integral of a closed four form over a four manifold whose boundary is M2-brane. So for instance, in flat space, the bosonic part of the super coframe and the four form appearing can be written in this form. The Vezumino term is important to ensure that the action has the so-called kappa symmetry, which is a local symmetry. And it is essential to reduce the independent degrees of freedom for fermions by 1/2 so that on shell the bosonic and fermionic degrees of freedom match. So it can be written in this form, where gamma can be thought of as a fermionic project expressed in terms of 11D gamma matrices and determined by the M2-brane. Another important property of M2-brane action is the so-called double-dimensional reduction. Namely, one can consider an 11D background compactified on a circle and also assume that the rest of the fields are independent of the coordinate in the circle direction. Then one can consider M2-brane in this background and assume that it wraps the circle and also fix part of the Wald volume diffeomorphisms by just identifying one of the directions of M2-brane with this circle direction and requiring that the rest of the directions are independent of this Xi2. Then one can perform a what is called double-dimensional reduction. It is reduction in both target space from 11D target space to type 2A target space, and also reduction on the Wald volume theory of M2-brane, which just gives the Green-Schwarz action in this type 2A background. Although there is a relation between Green-Schwarz action and M2-brane through this double-dimensional reduction, the quantization of small M2-branes is much more subtle. Well, for instance, the theory is nonlinear. However, one can argue that there is an analog of Lycon gauge for M2-brane in which there is a relation to quantum mechanics of ND0 branes, which suggests that the theory of small supermembranes has a gapless spectrum. Another problem is apparent non-renormalizability of M2-brane action, and in fact, it was discussed in a recent paper by Bikaria, Roiban, and Zeitlin, in which they considered 2-to-2 scattering S matrix for M2-brane, which is in flat space, and they considered this matrix for fluctuations around this M2-brane. And what they found is that it contains a genuine UV divergence at two-loop order. This, however, doesn't mean that other observables, as for instance partition function for M2-brane in AES space, will be UV divergent. In this talk, I will focus on M2-branes in ADS4A7 background, and I will consider semiclassical expansion around classical solution with non-degenerate metric. And I will also consider one loop order which is UV finite, so these problems will not appear there. So to obtain at one loop order semiclassical expansion, it's just enough to consider a quadratic action for both boson and fermions. The bosonic quadratic action can be written in this way, where there are F4 terms due to interaction with Ramon-Ramon 3 form, and the rest can be written in this way, where everything is expressed in terms of geometric data, which includes Riemann tensor of the background, and also geometric data of the classical surface, which is extrinsic curvature K, and also derivatives become derivatives in the associated normal bundle. The fermionic part can be written like that, where the derivative is just the pullback of 11D killing spinor derivative, and here gamma appears just as a result of kappa symmetry at the quadratic order. A convenient choice to fix this kappa symmetry is to set gamma theta to minus theta. So then the semiclassical expression, for instance, for a partition function takes the following form. There is a classical exponent, then there is one loop piece coming from operators in quadratic action, and then there are higher loops terms. So this semiclassical approach has been tested for several quantities. Maybe I should also mention that here usually you have M2-brane in some curved background, so you have a scale, for instance, as radius of ADS or S7, and you can introduce effective tension, which includes this scale. So the expansion then is in terms of the effective tension. So this semiclassical approach has been tested for several quantities for which the result is known from the gauge side, which includes expectation value for 1/2 BPS circle Wilson loop in ABJM theory, associated with it Bremsstrahlung function in ABJM theory, and also instanton contribution to the free energy on 3 in ABJM theory. And also, in the case of 6D2,0 theory, this includes surface defect conformal anomaly and giant graviton contribution to superconformal index. So in the rest of the talk, I'll primarily focus on ABJM theory. So let me just review some basic facts about this theory. So this is n equals 6 superconformal theory with the gauge group UN times UN. It has Chern-Simons level k and minus k. So in the superfield components, it can be written in the following way, where there are 4 bosons in B fundamental representation of the gauge group, and 4 fermions in the B fundamental representation of the gauge group. And bosons acquire sextic potential, while there is also mixed potential between bosons and fermions, which is quartic. The Chern-Simons level appear as an overall factor, k, so it can be considered as Young-Mills coupling in this theory. So one can define associated tooth coupling as a ratio of n and k, and consider the corresponding tooth limit. For k greater than 2, the global symmetry is just OSP 6,4, which is superconformal symmetry in this case, and there is also extra U1 baryonic symmetry, under which fields in B fundamental representation acquire charge +1, and fields in anti-B fundamental representation acquire charge -1. However, in the rest of the talk, I'll consider operators which have 0 charge under this one U1 baryonic symmetry, so this will not be that important, and I will assume that the Chern-Simons level is greater than 2, so there are no supersymmetry enhancements. So the dual gravitational description is in terms of M theory on ADS4S7 background. So this background can be thought of as a near-horizon limit of M2-Branes solution discovered by Duff and Stelle, which is just ADS4, well, the near-horizon limit of this solution is ADS4S7, while the orbifold action can be easily understood in the Hopf vibration coordinates of S7. Well, in these coordinates, the angle along the Hopf fiber, well, here it is called phi, and the orbifold action is such that it is identified with the period 2π/k. So I can just reabsorb this k into the metric by rescaling this coordinate, so that the 7th part can be written in this way, where A is just one form on CP3 such that its differential is Cayley form on CP3, and there is also non-zero Ramon-Ramon form such that F4 is proportional to the volume form on ATS. So one can consider also reduction to type 2A theory. This is done by taking the radius of this 11D circle to be small, and in this case, the type 2A theory is weakly coupled. The background is just ADS4 CP3, while the radius of ADS measured in string units is proportional to the square root of lambda. So then, if we consider M2-Brane in this background, its effective tension then just proportional to square root of nk. So if we want to consider large tension limit, effective tension limit, we can fix k and consider n to be large. So then observables in this semiclassical M2-Brane expansion will have the following form, where there is a classical piece, then there is one loop part and higher loops part in principle. So the key features is that we consider M2-Branes which wrap a 11-dimensional circle. This means that fluctuations on the surface can be expanded in Fourier modes with respect to this 11-dimensional circle. The topology of the M2-Brane would be some 2-dimensional worldsheet times a circle. So expansion in Fourier modes effectively introduces a tower of Kaluza-Klein modes on this worldsheet. The masses of these Kaluza-Klein modes would be then just proportional to the Chern-Simons level k, and here L is just an integer labeling these Kaluza-Klein modes. If we want to take type 2A strength limit, we can set k also to be large, and in this case, we can just discard all Kaluza-Klein modes and obtain just like the fluctuations would be just the same as for type 2A, Green-Schwarz string, and the expression the expansion can be done in terms of effective string tension now, which is, again, just proportional to the square root of lambda. So then the idea is that if you include these Kaluza-Klein modes, you will be able to get 1/k corrections, which are the same as G-string corrections. And these Kaluza-Klein modes appear from M2-Brane perspective. So the simplest, well, not the simplest, but one of the setups where this can be tested is the 1/2 BPS Wilson loop in ABJM. There is an exact form for Wilson loop from localization together with the Fermi-Gauss techniques so that the expectation value for Wilson loop can be expressed in terms of the Airy functions, and there is also 1/sin in front. So by fixing k and setting it to be greater than 2 and expanding this expression for large n, one can obtain just the following part. And here there is like exponent 1/sin, and then there are 1/square root of n terms. It is interesting that the same expression can be written in terms of effective string tension. And in this case, it obtains the following form. And it suggests interpretation that there is a classical M2-Brane piece, then there is one loop factor, and then there are high loop corrections. And indeed, as was discussed in the paper by Giombi and Zeitlin, one can consider a classical M2-Brane, which is ADS2 inside of ADS4, and it also wraps a Hopf circle of a 7. And one can reproduce both the classical part and one loop term by considering this M2-Brane. So the classical piece is given just by the wall volume of this M2-Brane upon regularization of ADS2 volume by -2 pi, which is a standard thing. And masses for fluctuations which appear, well, Kaluza-Klein masses, can be written in this way. There are two modes for bosons which come from directions orthogonal to ADS2 inside of ADS4, where L equals to 0, these are just two ADS modes with mass squared equals to 2, while the shift appeared due to interaction with the Ramon-Ramon form, and this interaction is non-zero only if you include the non-zero Kaluza-Klein level. Similarly, there are 6 modes which correspond to the directions in CP3. As one may expect, when L equals to 0, these are 6 massless modes, but they also are getting shifted for M2-Brane due to non-trivial connection in the normal bundle. So similarly, one can obtain masses for fermions, and it is interesting to note that they can be compiled into n=1 supermultiplets on ADS2. Well, they can be paired into n=1 supermultiplets on ADS2, and this seems to follow just from the fact that this M2-Brane preserves part of the supersymmetry of the target space. So it is translated on the supersymmetry on the wall sheet. So then one can compute one loop determinant for fluctuations, for instance, by using spectral zeta function, and it just reproduces the following, the 1/sin term. So everything matches. So apply the same setup for non-BPS quantities. We follow the same steps. Namely, we consider M2-Brane wrapping a Hopf circle. When we reduce this M2-Brane to 2D wall sheet, we have some type 2A string, which is dual to an operator on the gauge side. And type 2A string and its semiclassical quantization reproduces the planar part, while including Kaluza-Klein modes on this M2-Brane will give you non-planar corrections. So one of the simplest examples where it can be done is the so-called null-cusp anomalous dimension. It can be defined in the following way. So we consider a twist tool operator with large Lorentz spin, and in this case, the anomalous dimension grows logarithmically with the Lorentz spin, and the function which appears in front is what we refer to as the cusp anomaly. Just maybe as a comment, like as was mentioned in the previous talk, you can define null cusp anomaly in terms of the Wilson loop with null cusp, but these two definitions are just related to each other. So the planar part is controlled by integrability, and for instance, with Wick and Strock coupling, it can be expressed in terms of interpolating function in BGM, which appears in the Magnon dispersion relation. It is also interesting to note that The cusp anomaly in ABJM can be related to the one in n equals 4 CPM mills by the following identification of the parameters. And the interpolation function itself was proposed to have the following exact form by comparison of 1/6 BPS Wilson loop, for which the expression is known from localization also, and the slope function. So at strong coupling, the interpolating function takes the following form, and the dual description in terms of the strings is the so-called infinite folded string. So this string is stretched along ADS direction of ADS4, and it also rotates at the S1 boundary of ADS. The analogous construction in terms of Gubser-Klebanov-Polyakov string in ADS5. So from string perspective, the cusp anomalous dimension was computed up to 2-loop order, and the result just matches localization predictions. Here, k is the Catalan's constant. So to consider M2-Brane, we just uplift the solution by wrapping M2-Brane on the Hopf circle. In this case, the fluctuations, well, the classical energy would be just the same as for type 2A string, but the interesting question is, what do you get from one-loop expressions which contain these Kaluza-Klein modes and lead to non-planar corrections? So masses for fluctuations appear quite similar to those in the case of the Wilson loop, though the two bosonic masses are just a bit shifted due to rotation of the string. So then one can compute, since the string is infinite and the induced metric is flat, one can also expand the fluctuations in terms of the continuous momentum corresponding to this infinite direction. So to compute one-loop energy, one has to just take the integral of this continuous momentum and sum over Kaluza-Klein modes, which leads to the following expression for the cusp anomaly. So the second line from the bottom is just the planar part, which matches the type 2A string, and the bottom line is just what you get from including these Kaluza-Klein modes. And they contain 1 over non-planar corrections due to this 1 over k squared appearing. So there is a generalization of the story if you consider the so-called generalized cusp anomalous dimension. On the string side, this corresponds to the same infinite folded string, but you can also add momentum to the string in CP3 direction. A convenient limit one can consider if one takes both spin and momentum to be large, but at the same time fixes the ratio of log S and J. In this case, the classical string or M2-Brane energy can be written in this way, where there is extra dependence on this parameter x appearing. And again, the generalized cusp anomalous dimension is then defined just by the function which appears in front of this logarithm. So there is also relation to the n equals 4, to the string in ADS5 S5, where one can consider an analogous solution, and this relation can be expressed in this way. So the calculation in this case for a cusp anomaly is a bit more involved, as one has to, the modes that you appear, you cannot obtain the masses for Kaluza-Klein modes explicitly, but you can do some tricks to obtain this expression in terms of x and the non-planar correction of this form. So another set of solutions one can consider is the so-called circular spinning strings. For instance, one can consider a string which has two momenta in CP3 directions. And in fact, there are physically two distinct types of this solution. The one is so-called fast string or long string. It is called so because it has a rigid size, and this size is independent of momenta of this string. So one can consider a limit when the momenta is large. And in this case, the classical piece together with one loop part from the string has the following form, where C1 is just some constant. And one can also consider one loop correction, and in this case, it also appears, the leading term appears as 1 over k squared. It is called so because it is stabilized by its own rotation. So when you set its momentum to 0, the string shrinks. So it's also reflected in the classical energy of this string, which has a similar form as in flat space. And for this solution, you can also consider a small, small momentum limit. And in fact, this solution wasn't discussed in the case of ABJM, but it was discussed in the case of ADS5S5, and the one-loop calculation that you can done, for instance, by considering M2-Brane and discarding Kurlyand momentum is similar to the ADS5S5 case. So then you can include, as I mentioned, Kurlyand modes from this M2-Brane and obtain the following non-planar correction. And what's interesting is that you can take the flat space limit for this solution, in which the string, or like the string becomes just a string rotating in two orthogonal planes, while M2-Brane analog wraps some circle in the flat space. So in this case, you can see that there is a non-zero correction appearing, which can be interpreted as torus correction. And in fact, it's not surprising, as for such semiclassical states, one can compute two-point torus diagrams and obtain both real and imaginary corrections. Real part was computed for specific average states, so it's really hard to compare with this particular circular string. But one may expect an imaginary part in this case, and the imaginary part is responsible for the decay of such string. However, we do not see it here from this semiclassical approach, but it may appear from the resummation of higher loops. So, and similarly, one can consider circular spinning M2-Branes, which have both momentum in CP3 and spin in ADS parts. And here is also the non-planar correction that we obtain from M2-Brane. So maybe let me conclude. So in this talk, I have discussed how M2-Brane, how you can go beyond supersymmetry observables by considering M2-Brane, which generalizes string solutions. And this approach is based on the fact that there is a match between M2-Branes and the results from localization, which appear for supersymmetric quantities. It is interesting to ask whether this match will follow if you consider higher loops corrections. For instance, for 1/2 BPS Wilson loop in ABJM, there is also, like, the expansion in terms of effective tension suggests that there should be a higher loop, like two-loop term, which is non-zero. There has been also recent works by Gauterson and van Muyden, which suggests that, in fact, this higher loops term should disappear if you interpreted the semiclassical M2-Brane partition function as something that gives you not expressions in the canonical ensemble, but in grand canonical ensemble in BGM, which is used in the Fermi-Gas approach. But a priori, it is unclear why it may happen here. So for n equals 4 separating mills, you can ask the same question. Here I wrote down the expression, which is in fact valid in the planar limit when n is taken to be large, while for general lambda and n, it is in terms of the expression is in terms of Laguerre polynomials. But anyway, you can still expand this expression for large lambda, which gives you effectively expansion in terms of the effective string tension. And you can ask whether you can obtain higher loops by considering type 2b string in the ADS5S5 background. So again, the first terms, like 1 over g string, can be interpreted as a disk partition function. There is a classical piece. This square root of effective string tension appears from regularization of determinants. But then there should be some higher loop term appearing from semiclassical type 2b string. So this is all part of the future work. Okay, thank you.
Questions? Hello? do. Yeah, it takes some time. So what was my question? Like, at which order mixing with double traces or triple traces will become important for this type of calculation?
At which order mixes with double traces or single traces? That's a good question, but I think at least the leading part would appear just from M2-Brane calculation. It's really hard to say for me at which order you would appear mixing from other operators.
And then, so another question. So
and it also happens at strong coupling. So I mean, I'm not sure where the.
Well, strong is probably when there will be like lots of stuff it mixes with, right?
Well, at least again, the idea is the following: you have a match for supersymmetric quantities like BPS Wilson loop of free energy. You can argue that this happens there just because of supersymmetry. But the idea is that M2-Brane plays a more fundamental role, like the same role as type 2A string. So the idea is that you can consider the same semiclassical approach, and it, for some miraculous reason, also resounds higher corrections from type 2A string.
Just say for Kanish in n equals 4, right? If you look at the plot, then it's not even clear that 1/n expansion at strong coupling makes sense. In a sense, there is a accumulation of singularities, right? Because each time it mixes with double trace, there is a pole in 1/n squared term.
Well, yeah, I agree that this is subtle, but again, this is a result, again, not for n equals 4 symplectic mills. It's hard for me to say what will happen in this case because I don't have M2-Brane description in n equals 4. But here, this is a ABJM case, so I again understand that there are less results known from the gauge theory, what will happen with anomalous dimensions. But again, this is something that can be done at ease in a way, and this gives you some predictions that, again, should be checked.
Then like another question, so assume you consider general finite gap string solution. Then in principle, obviously, classical spectrum is continuous, but it's quantized quasi-classically by imposing that like integrals around cuts, like filling fractions are integer, right? This results in a discrete spectrum in the classical limit. But now, when you add some corrections, probably you like break essentially integrability, then the question is whether this Born-Sommerfeld kind of quantization, which is based on classics, whether it should also receive some corrections on the right-hand side.
Yeah, I agree, and that's why one of the future goals is to consider higher loops just for BPS quantities to see if this approach can be, like, if this semiclassical approach holds for higher loop corrections.
About the first question, it's a question which operator corresponds to that solution.
First question.
Legitimate question. First question was about mixing. So the claim is not that this classical solution corresponds to single trace, but to some particular state.
But you probably want to compute primary operator, right? Not a particular single trace.
About the second, semiclassical quantization will be exactly the same. It has nothing to do with integrability.
But integrability allows you to quantize this infinitely many of integrals around different cuts, but probably this disappears once you... Of course, like for folded string, there is only essentially one cut due to the symmetry, so it probably is fine. But if it's multi-gap solution, I don't know. There could be some subtle corrections on how like extra.
Valentina?
Wait. Maybe you mentioned the beginning, but did you try also to look for this half BPS?
Sorry, can you speak a bit louder?
Sorry. Half BPS Wilson loop in 2,0.
Half
dimensional conformal field theory. Did you?
Half BPS Wilson loop in 2,0. That's a good question. I'm not sure whether this was computed from M2-Brane, because in 62,0 M2-Brane appears as contribution to as a contribution, giant gravity contribution to the superconformal index, and also as a conformal defect anomaly. But I'm not sure that the calculation is done for Wilson loop in this case.
About next term, subleading
Yeah,
term.
if you're looking at the one
Yeah,
over.
that would be interesting question.
You mean like some, non-perturbative correction to the Wilson loop in terms of M2-Branes? That's what you mean?
Yeah, because
Yes, you can ask actually the same question not in 6D 2.0 theory, but in ABJM theory, because this expression, for instance, in terms of the Airy function, it captures not just perturbative corrections in 1 over n. So in principle, you may also have non-perturbative corrections the same way you have for free energy. In this case, you can also ask whether these non-perturbative corrections can be captured by some semiclassical M2-Brane.
No, I guess the question is about 2.0, which is related to 5-dimensional.
Yeah.
Okay.
Yeah.
Because if you go to 5 dimension, then it's not conformal and
Okay,
it's
yeah.
a bit more tricky.
Yeah, I see.
Okay.
Maybe one more question. Okay, if no further questions, let's thank Stefan again.